600 light-years away, a star 1,000 times wider than ours, is bleeding heat into the void, and its death has already begun. But Betelgeuse is only the doorway. Past its dying glow lies a wake of fire stretching 4 light-years wide, twin planets drifting alone without a parent, a star so vast light needs hours to cross it, and a void of pure nothingness 800 million light-years across. If this kind of cosmic exploration grips you, hit subscribe and stay close, because what waits beyond Betelgeuse should not exist. We begin. Look up at Orion in winter, and you will find a red ember burning on his shoulder. That ember has a name, Betelgeuse, and it is dying right now, in front of our eyes, in slow motion that takes thousands of years to play out. Betelgeuse sits roughly 650 light-years from Earth. Every photon hitting your eye tonight left the star around the time medieval Europe was building cathedrals. You are not looking at the present Betelgeuse. You are looking at a ghost of a star that may already be gone. Now imagine its size. If you placed Betelgeuse where our home star sits today, its surface would swallow Mercury, Venus, Earth, and Mars. It would keep going. Its outer edge would push past the asteroid belt and stretch toward the orbit of Jupiter. Picture that. An entire inner solar system, including the planet you are standing on, vanishing inside a single star like a marble dropped into a furnace. Astronomers estimate Betelgeuse holds more than 10 times the mass of our home star, possibly 20 times. Its diameter reaches nearly 900 times wider. Yet despite all that bulk, it is light. It is bloated. The outer layers have puffed outwards so dramatically that the gas there is thinner than a vacuum chamber on Earth. You could stand at its surface if you somehow survived the heat, and barely feel any matter beneath your feet. Here is the strange part. Betelgeuse is only about 10 million years old. Compared to our own home star at nearly 5 billion years, Betelgeuse is a newborn, a toddler, and yet it is already in the final stages of its life. Why? Because massive stars burn fuel like wildfires. The bigger the star, the faster it eats. Betelgeuse devours hydrogen at such a violent rate that it has already moved past hydrogen, past helium, and is now fusing heavier elements deeper inside its core. Each new fuel burns hotter and faster than the last. When the core finally runs out of options, the inside collapses, the outer layers crash inward at a fraction of light speed and rebound in an explosion brighter than billions of stars combined. A supernova. Astronomers say this could happen tonight, or in 100,000 years. Nobody knows. The signs that warn of a supernova travel slower than the explosion itself, which means we will simply see the sky light up one evening, and Orion will lose his shoulder forever. But Betelgeuse is doing something else right now that fascinates scientists. It is dimming, then brightening, then dimming again. In late 2019, the star lost almost 2/3 of its visible glow. Hubble caught the cause. A massive cloud of plasma erupted from its surface, expanded outward, cooled, and formed an enormous curtain of dust that blocked our view. The star burped its own atmosphere into space. This is not normal stellar behavior. This is a star unraveling. Its surface bubbles with convection cells the size of our entire home star, and each one churns hot material from deep within toward the outside. And while Betelgeuse seems to sit still in the night sky, it is not still at all. It is racing through space at terrifying speed, leaving behind a wake of cosmic fire most people never knew existed. Betelgeuse is running, not drifting. Running, the star tears through interstellar space at roughly 18 miles every second. That is around 65,000 miles per hour, faster than any rocket humanity has ever built. And as it races, it leaves behind a structure most people have never heard of, even though it is one of the most violent features in our local galaxy. Astronomers call it a bow shock. Picture a speedboat cutting across a still lake. Water piles up at the front, forming a curved wave that arcs out behind the hull. Now replace the water with thin clouds of hydrogen gas, freezing dust, and charged particles. Replace the boat with a star nearly 900 times wider than ours. The result is a shockwave so massive it stretches more than 4 light-years across the front of Betelgeuse. 4 light-years? That is roughly the same distance between our home star and the nearest star to us, Proxima Centauri. The wake of one star spans the gap between 2 solar systems. This bow shock was first imaged in 1997, and the data has only grown stranger since. The shock is hot, glowing in infrared light. It pushes outward as Betelgeuse plows forward, compressing the thin gas of interstellar space into a curved glowing arc. From our viewpoint on Earth, it looks like a flaming hood ornament leading the dying giant through the dark. Where does the material come from? Betelgeuse is bleeding. The star ejects its own outer layers at around 11 miles per second, throwing gas and dust into space in a constant stellar wind. That ejected material slams into the cold interstellar medium ahead of it, and the collision generates the bow shock. Heat, pressure, light, all of it visible to telescopes designed to see in wavelengths your eyes cannot detect. Now think about scale. Our entire home solar system, including the orbit of Pluto, would fit inside that bow shock thousands of times over. You could drop hundreds of star systems into the curved wave of compressed gas in front of Betelgeuse, and they would vanish like pebbles thrown into a tidal wave. Astronomers estimate the bow shock is less than 30,000 years old. Geologically speaking, on a cosmic timescale, that is yesterday morning. Before that, Betelgeuse was somewhere else in the galaxy, traveling a different path. Some event ejected the star from its birthplace and sent it tumbling through space alone. NASA scientists believe Betelgeuse came from the same hot region that produced the stars of Orion's belt. It is a runaway, a fugitive star. That detail changes how you should picture the night sky. Betelgeuse is not a quiet ornament hanging above winter. It is a runaway giant dragging a 4 light-year wave of compressed fire behind its leading edge, racing through the galaxy on a trajectory it did not choose. And here is what astronomers cannot quite agree on. There is something ahead of Betelgeuse, a barrier, a wall of dense interstellar material that the star is heading directly toward. Researchers predicted years ago that within several thousand years, Betelgeuse would crash into this wall. What happens when a dying supergiant slams into a cosmic wall has never been observed in human history. Betelgeuse is on a collision course. Not with another star, not with a planet, with something far stranger, a vast, dense ribbon of interstellar dust, hanging silently in its path. And in roughly 5,000 years, the runaway giant will hit it. In 2013, a team studying infrared images from the Herschel Space Observatory spotted something unexpected just ahead of Betelgeuse. A long, thin, almost ruler-straight bar of dust, glowing faintly against the cold background of space. At first glance, the bar looked like a magnetic filament, some kind of cosmic thread, but then they measured its position relative to Betelgeuse's trajectory. The bar sits directly in the star's path. Astronomers do not know what the bar is. 2 leading theories exist. The first says it is a filament of gas and dust shaped by the magnetic field of our galaxy, and Betelgeuse just happens to be heading toward it, by coincidence. The second theory is more unsettling. Some researchers believe the bar may be the edge of a much larger interstellar cloud, possibly material left over from a previous wave of star formation in the region. If true, Betelgeuse is about to slam into the leftover graveyard of older suns. The collision will not be quick. Stars do not crash into dust the way cars crash on highways. The encounter unfolds over thousands of years, like a continent grinding into another continent in slow motion. But the effects will be dramatic. When the bow shock of Betelgeuse, that flaming wake stretching 4 light-years across, reaches the dust bar, the compressed gas will pile up against the wall. Pressure will spike. Temperatures will soar. The leading edge of the shock could light up in infrared and possibly even visible wavelengths, becoming a new feature in the night sky long after our great-great-great descendants are dead. Then the dust itself will be heated, agitated, and possibly ignited into glowing structures. Some computer simulations suggest the encounter could trigger small bursts of star formation in the disturbed material, as gravity pulls clumps of agitated gas together. In other words, the death march of Betelgeuse may seed new stars before the giant itself ever explodes. There is one more strange detail. The dust bar sits at a distance scientists initially measured at less than a quarter of a light year from Betelgeuse's leading edge. That sounds enormous, but for a star traveling 65,000 miles per hour, that gap closes faster than you would expect. The first contact between the bow shock and the bar may begin in just over 5,000 years. The full encounter will continue for tens of thousands of years after that. Scientists are confident the dust bar exists. The collision timing is a strong projection based on current motion. The full cosmic consequences remain a theory. Imagine standing on Earth 10,000 years from now, looking up at Orion. The shoulder of the hunter no longer holds a quiet red star. It glows brighter, stranger. A swelling cloud of disturbed material wraps around the star, lit from within by the violence of the collision. The constellation we have known for 40,000 years of human history, the same shape painted in caves and carved into temples, will be transformed. But Betelgeuse is only one player. Behind it lies something much larger. If you could strip away the visible light from Orion and see only what lies behind the constellation in cold infrared, the entire sky would change. Where you used to see 7 bright stars forming a hunter, you would see something monstrous, a vast, churning cloud larger than anything else in our local cosmic neighborhood. Astronomers call it the Orion Molecular Cloud Complex, and Betelgeuse is sitting right in front of it. The complex stretches more than 1,000 light-years across in one direction and 400 light-years across in another. To put that in scale, our entire home solar system, from the home star out to the edge of the Oort cloud, fits inside the complex roughly 100,000 times over. It is so vast that the constellations of Orion and Eridanus both sit embedded inside its outer edges. What is it made of? Cold gas, mostly hydrogen, with traces of helium, dust, and complex molecules. The temperatures inside parts of the cloud drop to around -400 degrees Fahrenheit, almost as cold as anything can get in this part of the galaxy. And yet, paradoxically, this freezing darkness is one of the most active star factories in the entire Milky Way. Stars are forming inside it right now, thousands of them. Here is how it works. Inside the cloud, gravity slowly pulls clumps of gas together. The clumps grow denser, they heat up as they compress. After hundreds of thousands of years, the pressure at the center of a clump becomes high enough to ignite nuclear fusion. A new star is born. The newborn star fires radiation outward, blowing back surrounding gas, sometimes triggering even more collapse in nearby clumps. The process cascades. One star births dozens, dozens birth hundreds. Astronomers estimate the cloud contains enough raw material to build several 100,000 stars the size of our home star. Most of that material has not collapsed yet. It just sits there in the dark, cold and silent, waiting for the next gravitational push to begin its transformation into light. The cloud is also full of structures with names that sound like science fiction. Dark globules, Bok globules, cometary knots, molecular filaments. Each one is a different stage of the same process, gas, slowly organizing itself towards stellar birth. Some filaments are so thin they would look like spider silk if you could see them with your eyes, but each strand contains enough mass to build dozens of stars. The complex glows in infrared because the dust trapped inside absorbs the light from newly born stars and re-emits it as heat. To human eyes, the region looks dark and empty. To the James Webb Space Telescope, it lights up like a city seen from orbit at night, full of bright knots and tendrils of glowing structure. And here is the disturbing part. The Orion molecular cloud is moving. It rotates slowly, parts of it collide with other parts. Shockwaves ripple through the gas at speeds of several miles per second. These ripples compress new regions and trigger fresh waves of starbirth, century after century, for tens of millions of years. Inside the heart of this churning monster sits a region so violent, so blinding, that the radiation pouring out of it would sterilize a planet within minutes. The Trapezium cluster. Deep inside the Orion Nebula, 4 young stars sit clustered together in a tight diamond shape. They are called the Trapezium. From Earth, you can spot them in a small backyard telescope as 4 pinpricks of light at the heart of the nebula. They look harmless, almost peaceful. They are not. The Trapezium stars are some of the most violent newborns in our entire region of the galaxy. The largest member, called Eta Orionis C, is roughly 33 times more massive than our home star and burns at a surface temperature of nearly 75,000 degrees Fahrenheit. The energy pouring out of this single star is around 200,000 times brighter than anything our home star produces. That kind of brightness has consequences. Around the Trapezium, the radiation is so intense that it ionizes everything for light years in every direction. Hydrogen atoms get stripped of their electrons. The ionized gas glows pink and green in long-exposure photographs. This is the famous color of the Orion Nebula. You are not looking at gentle starlight reflecting off dust. You are looking at hydrogen gas being torn apart at the atomic level by ultraviolet radiation. Now think about where these stars formed. They were born inside the same cold, dark cloud we just talked about, the Orion Molecular Cloud. They condensed out of dense knots of gas, and the moment they ignited fusion, they began destroying their own birthplace. The radiation from the Trapezium is now hollowing out the inside of the nebula, pushing back the surrounding gas, carving a vast cavity where stars once formed in peace. If you could stand on a planet orbiting one of these stars, you would die before you finished blinking. The ultraviolet output alone would burn skin to bone in seconds. The stellar wind would strip the atmosphere off any planet within 100 million miles. There are no shields strong enough to protect biology from the conditions around Eta Orionis C, and yet, somehow, planets are forming there anyway. Astronomers using Hubble and the James Webb Space Telescope have found dozens of disc-shaped objects around the Trapezium. They are called proplyds, short for protoplanetary disks. Each one is a swirling pancake of dust and gas around a young star, the kind of structure that eventually condenses into planets. But these proplyds are not safe. The radiation from the Trapezium is evaporating them. You can see the disks being burned away in real time, with cometary tails of gas streaming away from each one in the direction opposite to the Trapezium. Some of these baby solar systems will not survive long enough to finish forming planets. Their disks will be stripped before any rocky world can condense. Others will manage to form, but with strange properties twisted by the constant blast of stellar wind from their massive neighbors. The Trapezium is also a binary nightmare. Most of the 4 stars have hidden companion stars, some so close they orbit each other in less than a few days. Gravity between the stars warps the entire region, pulling material toward and away from them in chaotic streams. This is what star formation actually looks like up close. Not gentle, not romantic, brutal, bright, lethal. But even the Trapezium is not the strangest thing in the Orion Nebula. Floating quietly nearby are objects that should not exist at all. In October of 2023, the James Webb Space Telescope sent back images that broke part of astronomy. Researchers studying the Orion Nebula spotted nearly 150 mysterious objects floating in the gas. Each one was roughly the mass of Jupiter, and each one was wrong. These objects are not stars, they are too small. A real star needs at least 80 times the mass of Jupiter to ignite fusion at its core. Anything less just sits there, glowing faintly from leftover heat. So scientists initially expected these objects to be brown dwarfs, the so-called failed stars. But the masses were even lower. Some were just 5 times the mass of Jupiter. Others were exactly Jupiter-sized. And they were not orbiting any star, they were drifting alone through the nebula. That alone is strange. Free-floating planet-mass objects exist throughout the galaxy. Sometimes a young solar system goes wrong, gravity throws a planet out, and the world wanders the dark forever. Astronomers have catalogued these rogue worlds before. Lonely, cold, but not unknown. Here is what made the Orion discovery shocking. The objects were paired up, 2 at a time, orbiting each other. The team named them JUMBOs, short for Jupiter Mass Binary Objects. Dozens of pairs scattered across the nebula, each pair held together by mutual gravity, slowly waltzing around their shared center in the freezing dark. According to current theories of how planets and stars form, these things should not exist. Planets form inside disks around stars. They are built from leftover material that did not fall into the star itself. So a planet without a parent is unusual but explainable. But 2 planet-mass objects, gravitationally bound to each other, with no star nearby, formed somehow in the wild gas of an open nebula. That breaks the model. One of the discoverers, Samuel Pearson at the European Space Agency, said in interviews that the objects should not exist. His exact reaction was disbelief. Heidi Hamel, a senior scientist on the Webb mission, said her response was just a string of confused questions about what they were even looking at. Scientists have proposed 2 main theories. The first says JUMBOs are ejected planets. They formed normally around stars in the Orion Nebula and were thrown out when their solar systems became unstable. Some pairs got tangled together during the ejection and are now bound to each other by gravity. The problem is, computer simulations of ejection scenarios rarely produce paired objects. Single ejections are common, pairs are vanishingly rare. The second theory says JUMBOs formed directly from the gas of the nebula itself, like tiny stars that ran out of material before they grew big enough to ignite fusion. This idea also has problems. Gas clouds usually do not collapse efficiently at such small masses. Something else has to be happening. Either way, the JUMBOs are real. They exist. The Webb data is solid. Scientists have not yet figured out how they got there, only that the cosmic process used to make them is not currently in any textbook. And they are not the only failed objects in this region. Behind every glowing star in Orion, there are dozens of dim, cold worlds you would never see with human eyes. For every bright star you can see in the night sky, there may be 1 or more invisible companions you cannot. They are called brown dwarfs, stars that almost made it, almost ignited, almost shined, but they fell just short, and now they drift through the galaxy as cold, dark, half-finished objects. A brown dwarf forms exactly the way a star forms. A clump of gas inside a molecular cloud begins to collapse under its own gravity. The clump heats up as it shrinks. The center compresses. Pressure climbs. But for a true star to be born, the core needs to reach about 18 million degrees Fahrenheit, hot enough to fuse hydrogen atoms together and release energy. That ignition is what makes a star a star. Brown dwarfs never get there. Their masses fall between roughly 13 and 80 times the mass of Jupiter, too heavy to be a planet, but too light to ignite hydrogen fusion. The cores reach only a few million degrees. Some brown dwarfs can briefly fuse a heavier form of hydrogen, called deuterium, or even fuse lithium for a short time, but these reactions sputter out within tens of millions of years. After that, the brown dwarf cools forever. Hubble surveys of the Orion Nebula in 2017 found the largest known population of brown dwarfs ever spotted in a single region. They sit scattered among newborn stars, glowing faintly in infrared, invisible to optical telescopes. Scientists also discovered 3 giant planets free-floating in the same survey, including 1 binary planet pair where 2 worlds orbit each other with no parent star in sight, similar to the JUMBOs, but found years earlier. Imagine what these objects look like up close. The the surface of a young brown dwarf would still be warm enough to glow a deep, dull red, not bright. More like the embers of a dying campfire. The atmosphere is thick with clouds. Some brown dwarfs have storms of molten iron raining down through layers of silicate vapor. Others have winds blowing at speeds that would shred a planet's surface if it tried to land. As they age, brown dwarfs cool. The dim red fades to maroon, then to a deep magenta only visible in infrared cameras. The very oldest brown dwarfs, billions of years old, are nearly invisible. They are called T dwarfs and Y dwarfs in classification systems. The coldest known brown dwarf has a surface temperature roughly equal to the temperature of a hot summer afternoon on Earth. Think about that. A failed star, larger than Jupiter, with the surface temperature of your skin. The galaxy may contain billions of these things. Some estimates suggest brown dwarfs outnumber regular stars in our local neighborhood. They drift between solar systems in numbers we cannot fully count because they are simply too dim to see at distance. If a brown dwarf was passing through our solar system right now, just a few light years away, we might not know it. Our telescopes would have to look directly at it in the right wavelengths to detect anything. The galaxy hides them well. Now picture this. You are standing on a hypothetical planet orbiting a brown dwarf. The sky above you is permanently dark. The brown dwarf glows a faint reddish purple, just bright enough to cast shadows. Day never comes, night never ends. The galaxy turns above you in eternal twilight, but not every dim object in Orion is failed and quiet. Some are being born under attack. Inside the Orion Nebula, the future is being murdered, specifically the future of dozens of young solar systems. They are called proplyds, short for protoplanetary disks, and many of them will not survive long enough to finish becoming what they were born to become. A proplyd is a flat, swirling disk of gas and dust around a young star. Our own home solar system started as one of these about 4.5 billion years ago. The disk slowly cooled, gas condensed, dust clumped together, and over millions of years, the leftover material assembled itself into planets. Earth, Venus, Jupiter, and the others are all the leftover lumps from that long process. Proplyds in the Orion Nebula are doing the same thing right now, but they are doing it under fire. The proplyds sit close to the Trapezium, the cluster of massive young stars we visited a few chapters ago. Those stars pour out ultraviolet radiation at intensities most planets could never tolerate. When the radiation hits a nearby proplyd, the outer layers of the dust and gas disks start to vaporize. The disk loses material into space. Long, glowing tails stream away from the proplyd, all pointing in the direction opposite to the Trapezium, like comet tails fleeing the heat. Astronomers have photographed dozens of these dying disks using Hubble and the James Webb Space Telescope. Each image is a frozen frame of a slow disaster. The proplyds look beautiful, tiny gold and red teardrops glowing against the pink background of ionized gas. But the beauty hides destruction. Here is the brutal arithmetic. A young star needs around 10 million years to build planets from its disk. The radiation from the Trapezium evaporates a typical proply in roughly 100,000 years, possibly faster for the closest ones. That is 1% of the time required for full planet formation. Most of these disks will lose their raw material before any rocky planet has a chance to condense. The smallest proplyds may form only 1 or 2 planets before their disks vanish entirely. The middle-sized ones might form a few, but the resulting planets will be smaller than expected, with thinner atmospheres and less water. Only the proplyds farthest from the Trapezium have any chance of forming full solar systems with diverse planet types. There is also the problem of orbital chaos. Even if a planet does form, the gravity of nearby stars in such a crowded region tends to disrupt orbits. Worlds get pulled into eccentric paths. Some get ejected entirely, becoming the rogue planets and duembios we discussed earlier. The Orion Nebula may be the source of many of those wandering worlds, born here, stripped here, thrown out here. Now imagine what the night sky looks like from a planet inside one of these droplets, if such a planet ever managed to form. There is no normal night. The trapezium burns overhead so brightly that the sky never really gets dark. Around you, the surrounding gas of the nebula glows pink and green in vast curtains. Other young stars dot the cosmic background. A planet here would never know true darkness. These dying disks are violent, but they are quiet compared to what some of the young stars themselves are doing. Some stars in this region fire jets of plasma so fast they tear through the surrounding gas like supersonic spears. Some baby stars do not just sit quietly inside their disks, they erupt. They fire massive jets of plasma out from their poles at speeds reaching hundreds of miles per second. Those jets slam into the surrounding gas of the nebula and create some of the most beautiful and violent structures in nearby space. They are called Herbig-Haro objects, named after the two astronomers who first catalogued them in the 1940s. In the Orion region alone, telescopes have spotted dozens of these jets. They look like glowing arrows shooting out of dark cocoons of dust, terminating in bright red and pink shock fronts where the plasma hits the surrounding cloud. Here is how a Herbig-Haro object forms. A young star, still buried inside its protoplanetary disk, is collapsing and feeding on material from the disk. As gas spirals down toward the star, magnetic fields tangle and twist. Some of the infalling material gets redirected, channeled along the magnetic field lines, and shot back outward along the star's rotational poles. The result is two thin, focused jets of plasma firing in opposite directions, like lasers from the top and bottom of the young star. These jets are not gentle. They travel at speeds of 200 to 400 miles per second. They are made of ionized hydrogen, sulfur, and other atoms heated to thousands of degrees. When the leading edge of a jet plows into the surrounding cold gas of the nebula, the collision ionizes the cold gas, creating shock fronts that glow brightly in red and green wavelengths. Some Herbig-Haro objects stretch for several light years from end to end. Their bow shocks form curved arcs where the plasma decelerates and piles up against the surrounding material. Along the length of the jet, you can see knots of brighter emission, places where the jet pulsed harder for a moment, sending a denser slug of plasma down the path. The jets are also evidence of something deeper. Stars do not just form and shine, they actively reshape the regions around them. A young star firing two Herbig-Haro jets is carving channels through its birth cloud, blowing back gas, sometimes triggering the collapse of new clumps where the shock waves compress the surrounding material. The jets help recycle the nebula. They redistribute energy and material, and they may even seed new star formation downstream of the shock front. Some Herbig-Haro objects do not last long. The jets only fire while the star is actively feeding from its disk. Once the disk is mostly gone, the jets shut off. The remaining shock fronts continue traveling for thousands of years, fading as they expand and cool, until eventually they dissolve into the surrounding gas and become invisible. What you see in any given image is a snapshot of a few thousand years of activity. And here is something to imagine. If you were on a planet near one of these jets, you would see two glowing beams arcing across your sky, terminating in bright red knots where the plasma slams into the surrounding gas. The beams would shimmer, pulse, brighten, and fade. Each pulse would represent a moment when the central star fed harder on its disk, sending a fresh wave of material outward. Not every dark structure in Orion is full of glowing jets. Some are just shadows, vast columns of dust silhouetted against bright nebulae behind them. And one of the most famous of these shadows is being eaten alive. About 1,500 light-years from Earth, just below the easternmost star of Orion's belt, a vast, dark column of dust rises out of an even darker cloud. Its silhouette is shaped like the head of a horse, ears tilted forward, mane curving back. You may have seen photographs. The Horsehead Nebula is one of the most photographed deep-sky objects in history. But the Horsehead is not just a beautiful shape, it is a battlefield. the dark column rises against a glowing red background of ionized hydrogen gas. That red glow is being produced by a hot young star called Sigma Orionis, which sits to the side of the column and pours out massive amounts of ultraviolet radiation. The radiation is ionizing the gas around the Horsehead, lighting the background pink and red, and it is also slowly destroying the column itself. The Horsehead is dying, eaten by ultraviolet light. Here is what is happening. The column is dense. Inside it sits a thick concentration of cold molecular gas and dust, partially shielded from the ultraviolet onslaught by its own opacity. The outer edges of the column, however, are exposed. The radiation hitting the surface heats the gas, breaks apart molecules, and slowly evaporates the outer layers into space. Astronomers call this process photoevaporation. Estimates suggest the Horsehead has roughly 5 million more years before the radiation strips away enough material to dissolve it completely. 5 million years sounds like a long time. On a human scale, it is unimaginable. On a cosmic scale, it is nothing. 5 million years is less than 0.1% of the age of the galaxy. The horse will be gone before our home star reaches the end of its main lifetime. But there is something fascinating happening inside the column. The dense interior is shielded from the radiation, and inside that shielded core, gravity is pulling clumps of gas together. New stars are forming right now, inside the Horsehead, hidden from view by the surrounding dust. The James Webb Space Telescope has imaged some of these embedded young stars, peering through the dust at infrared wavelengths to see what optical light cannot reach. So the Horsehead is doing two things at once. It is being slowly destroyed from the outside while quietly building new stars on the inside. The destruction and the creation are happening in the same place at the same time. By the time the column fully dissolves in 5 million years, the new stars will have ignited and emerged into the open, free-floating in the same region of space where their birth column once stood. Astronomers also see waves of pressure rippling along the surface of the Horsehead. The ultraviolet radiation does not just evaporate material evenly, it carves uneven patterns. Some areas erode faster than others. The shape of the horse changes over time. Slowly, the mane shifts. The ears curve. If you could watch the Horsehead for 1 million years, it would slowly transform, no longer recognizable as the iconic silhouette we photograph today. Just below the Horsehead, in the same general region, sits another nebula glowing brightly. Where the Horsehead is dark and being destroyed, this neighbor is bright, hot, and full of newborn stars. The Flame Nebula. To the eye, the Flame Nebula looks like a tongue of fire frozen in space. Streaks of bright orange and red gas split by a dark vertical lane of dust running through the middle. From a distance, it looks like someone took a match to the cosmic background and the flame was caught mid-flicker. The reality behind the image is even more dramatic. The Flame Nebula sits about 1,300 light-years from Earth, near the easternmost star of Orion's belt, the star called Alnitak. Alnitak is a massive blue supergiant, roughly 33 times the mass of our home star, burning at extreme temperatures. The radiation from Alnitak hammers into the gas of the Flame Nebula, ionizing the hydrogen, which then glows in the red and orange wavelengths we see in photographs. But Alnitak is only the trigger. The real action is hidden inside. Behind the dark lane of dust that splits the nebula in half, an entire cluster of young stars is forming. They are invisible to optical telescopes because the dust blocks visible light. Infrared telescopes, however, can see right through the dust. When the Spitzer Space Telescope first imaged the Flame Nebula in infrared, astronomers discovered hundreds of newborn stars embedded in the cloud, all between roughly 200,000 and 2 million years old. For comparison, our home star is about 4.5 billion years old. The stars inside the Flame Nebula are babies. Some of them are still surrounded by their protoplanetary disks, building planets right now. Others have just emerged and are now beginning to ionize the gas around them, contributing their own radiation to the glow we see. Astronomers also discovered something interesting about the cluster's structure. The stars at the center of the cloud are older than the stars at the outer edges. That is the opposite of what you would expect. Normally, star formation moves outward through a cloud, with the oldest stars at the original center and progressively younger stars further out, as the formation wave expands. In the Flame Nebula, however, the wave appears to be moving inward, possibly because the cloud is being compressed from the outside by pressure from Alnitak and other massive stars in the area. The dark lane that splits the Flame Nebula in two is a thick filament of dust and molecular gas, dense enough to block almost all visible light. Inside this lane, gravity is pulling new clumps of material together at this very moment. Future stars are condensing. Future planets are beginning to take shape. The lane is the most active part of the entire nebula, even though it looks like the deadest part in optical photographs. The whole structure is connected to the Horsehead Nebula and to other nearby clouds, all part of the same overall complex of star-forming regions in Orion. Material flows between these clouds. Stars born in one region drift into others. Radiation from one cloud erodes another. The entire neighborhood is one massive interconnected system, slowly cycling gas through stars and back into clouds over hundreds of millions of years. If you could stand on a planet inside the Flame Nebula, the sky would glow orange and red with ionized hydrogen. The dark dust lane would block out part of your view, and dozens of other young stars would shine around you. A surreal environment, almost alien in its strangeness. But not every nebula is on fire. Some are silent. Most nebulae glow because their gas is hot. The atoms inside them are ionized, electrons recombining with protons and emitting light at specific wavelengths. That is why the Orion Nebula glows pink, and the Flame Nebula glows red. Active emission. Hot gas, making its own light. M78 is different. M78 does not make its own light at all. It just reflects light from somewhere else. The nebula sits about 1,600 light-years from Earth, slightly higher in the sky than Orion's belt. Through a small telescope, M78 looks like a soft, fuzzy blue glow with two bright stars embedded in it. The blue color is the giveaway. Emission nebulae tend to look red or pink, because hydrogen emits strongly in those wavelengths. Reflection nebulae, like M78, look blue because dust scatters short wavelength blue light more efficiently than longer wavelength red light. The same effect makes Earth's daytime sky appear blue. So when you look at M78, you are looking at a giant cloud of dust, illuminated from within by a couple of hot stars, scattering their light back towards us in a soft blue haze. The two stars inside M78 are called HD 38563A and B. They sit close together near the center of the nebula. Both are hot enough to produce significant ultraviolet light, but not hot enough to ionize most of the surrounding gas. So the cloud does not glow on its own. It just bounces back the blue portion of the light from these two stars, like dust caught in a flashlight beam. But M78 is hiding things. Inside the dust, astronomers have found at least 17 Herbig-Haro objects, those plasma jets we discussed a few chapters ago. Each one comes from a young star buried in the cloud, firing its energy outward through the dust. Some of the jets escape M78 entirely and continue into the surrounding regions. The cluster also contains a number of T Tauri stars. These are very young stars, less than a few million years old, still in the chaotic phase of their early lives. T Tauri stars vary unpredictably in brightness, rotate quickly, fire flares, and have powerful magnetic fields. They are essentially adolescent stars, going through stellar puberty. M78 is part of a larger structure called the Orion Belt subgroup, which itself is embedded in the wider Orion molecular cloud. The dust in M78 is dense enough to obscure the stars behind it, creating sharp, dark lanes against the blue glow. Astronomers studying these dark lanes have detected complex molecules inside, including water, ice, methanol, and even simple amino acids. Amino acids are the building blocks of proteins, which are the building blocks of biology. M78 and other dust clouds in Orion contain the chemical raw materials that life on Earth was eventually built from. When our home solar system formed, the raw material came from a similar cloud, full of similar molecules. The chemistry of life is older than the planet you live on. Looking at M78 from Earth, you see a quiet blue glow. Looking at it up close, you would see freezing dust, hidden young stars, plasma jets, complex molecules drifting in the dark, and the slow assembly of future solar systems still hundreds of thousands of years away from ignition. But not everything in Orion is small or local. One feature wraps around the entire constellation in a giant arc. If you photographed Orion with a long-exposure camera and the right filters, you would see something most people never know is there. A vast, faint curved arc of red gas sweeps around the entire constellation. It encloses Orion's belt, the sword, the surrounding nebulae, and parts of the broader region. Astronomers call it Barnard's loop, and it is the fading scar of an ancient cosmic explosion. The loop spans roughly 300 light-years across. It would dwarf almost any other structure in our local part of the galaxy. From Earth, the arc covers an enormous portion of the sky, but it is so dim that it cannot be seen with the naked eye. Only long-exposure imaging brings it out clearly. What made it? Astronomers have a leading theory. Around 2 million years ago, a massive star inside the Orion region exploded as a supernova. The blast ejected enormous amounts of gas outward in a roughly spherical shockwave. As the shockwave expanded, it ploughed through the surrounding interstellar medium, pushing gas outward and compressing it into a hot shell. That shell, after slowly cooling and recombining over millions of years, became the glowing red ring we now see as Barnard's loop. If the theory is correct, the loop is essentially a fossil, the corpse of an explosion that shook this region of the galaxy long before humans existed. The original star is gone, probably collapsed into a neutron star or black hole. Maybe ejected from the region during the blast. We do not know exactly which one, but the loop is still expanding. The shockwave continues to push outward, slowly, as the gas cools and the pressure equalizes. Over the next several million years, the structure will continue to grow, eventually merging with the surrounding interstellar medium and becoming undetectable. There is also a second theory. Some astronomers believe Barnard's loop is not the result of one supernova, but of multiple supernova explosions over the course of millions of years. The Orion region is full of massive stars, and massive stars die fast. Several of them may have exploded in sequence, each one adding energy to the same expanding shell. The cumulative result would look essentially the same as a single large blast. Either way, the loop tells you something important about Orion. The constellation is not stable. Massive stars are forming, living, and dying inside it on relatively short timescales. The region has seen multiple violent events in the past few million years. The next supernova could be Betelgeuse itself, and when it goes, it will add another shockwave to the long history of explosions that have shaped this neighborhood. Imagine what that future blast will look like from Earth. When Betelgeuse finally collapses, the supernova will briefly outshine the entire planet of Venus in the night sky. It will be visible during the day. For a few weeks or months, Orion will have a second daytime light source on his shoulder, fading slowly over months and years. Then the shockwave from the explosion will begin its expansion outward, eventually adding a new arc to the cosmic neighborhood, just like Barnard's loop did 2 million years ago. And all of this is happening inside one tiny corner of one arm of one galaxy. Step back further, and you find yourself looking at the spiral arm we live in, with Orion sitting near its outer edge. When people talk about the Milky Way galaxy, they usually picture a flat spiral with sweeping arms. That picture is roughly right, but it misses something important. Between the major arms, smaller branches stick out, half-arms, spurs, and our home solar system sits inside one of them. It is called the Orion Spur. It runs alongside the larger Sagittarius arm, and the constellation we have been exploring sits in the same region of space. The spur is roughly 3,500 light-years wide and 10,000 light-years long. That sounds enormous, and it is, but compared to the major arms of the Milky Way, it is small. The Sagittarius arm and the Perseus arm dwarf it. The spur is more like a side branch poking out between two major highways. But what makes the spur interesting is what lives inside it. Our home star, the constellation Orion, the Pleiades, Sirius. Almost every star you can see with your naked eye on a clear night sits inside the Orion Spur. Your entire visible sky, the patterns ancient cultures named after gods and heroes, is essentially a tiny snapshot of one local neighborhood inside one branch of one galaxy. Travel beyond the spur and the sky changes. From a planet inside the Sagittarius arm, the constellations would be unrecognizable. None of the patterns we know would exist. New stars would dominate the view. The belt of Orion would be lost in the distance, just one more dim cluster among thousands. The spur is also moving. Like all parts of the galaxy, it rotates around the central black hole of the Milky Way. Our home solar system completes one full orbit around the galactic center roughly every 230 million years. That orbit is called a galactic year. Our planet has only existed for about 20 galactic years total. Recorded human history, all of it, fits inside about a 50,000th of a single galactic year. The spur is also passing through cosmic features as it rotates. We are currently inside what astronomers call the local bubble, a roughly spherical region of low-density gas, about 1,000 light-years across. The bubble was probably carved out by a series of supernova explosions over the past 10 or 20 million years. So our solar system is sitting inside a hot, low-density cavity left behind by old stellar deaths. Once again, the ghosts of long-dead stars shape the environment we live in. What lies at the far edge of the spur is harder to map. Dust and gas obscure our view of more distant stars. Telescopes have to work hard to peer through the murk. But what we do see suggests the spur thins out toward its outer end, gradually merging with the broader space between the major arms. Beyond that, the Sagittarius arm sweeps past, full of dense star clusters, glowing nebulae, and supernova remnants. Most of the spur, including parts we cannot easily see, contains massive stars that dwarf Betelgeuse. Stars so big that even the dying giant on Orion's shoulder looks small in comparison. The first of these is hiding in plain sight, embedded in the same constellation we have been exploring this entire video. If you trace Orion's head, the small triangle of stars above his shoulders, you find a star called Lambda Orionis. Most people glance past it. It is not as famous as Betelgeuse or Rigel. It looks like a single average star to the naked eye. But Lambda Orionis is anything but average. It is a colossal, hot, bloated giant, and it is unstable. Lambda Orionis sits roughly 1,300 light-years from Earth, almost twice as far as Betelgeuse. Despite that distance, it is bright enough to be visible in the night sky as a third-magnitude star. The reason is its sheer luminosity. Lambda Orionis pours out roughly 160,000 times more energy than our home star. It is also massive, around 28 times the mass of our home star, and burns at a surface temperature of about 60,000 degrees Fahrenheit. That surface temperature matters. Hot stars, the kind that look blue or blue-white in photographs, burn through their fuel faster than cooler stars. The hotter the star, the shorter its life. Lambda Orionis is only a few million years old, and it is already nearing the end of its main stable lifetime. Within a few more million years, it will swell into a red supergiant similar to Betelgeuse, before eventually exploding as a supernova. around Lambda Orionis is something even stranger. The star is surrounded by a vast, faint, glowing ring of gas called the Lambda Orionis Nebula. The ring stretches more than 150 light-years across. It is the fossil of an old supernova, possibly a companion star to Lambda Orionis, that exploded several million years ago and left behind this expanding shell. The original blast carved a cavity around Lambda Orionis, and the surviving star now sits inside that cavity, illuminating the inner walls of the bubble. Inside the cavity, dozens of young stars are forming. They are part of the Lambda Orionis cluster, a stellar association that may have been triggered into existence by the same supernova shockwave that created the surrounding nebula. The shockwave compressed nearby gas, gravity took over, and a wave of new stars condensed in its wake. Those stars are now visible as a loose cluster around the central giant. There is a darker theory about Lambda Orionis. Some astronomers believe the star is a runaway. Like Betelgeuse, computer simulations suggest Lambda Orionis may have been ejected from a tighter binary system long ago, possibly when its companion went supernova. The kick from the explosion sent Lambda Orionis tumbling outward, and it now drifts through space at high speed relative to the surrounding stars. If true, the central giant we see today is an orphan, born inside a different system, hurled out by the death of its sibling, continuing alone towards its own eventual destruction. Lambda Orionis itself is also unstable in subtle ways. Its brightness varies slightly over short timescales, suggesting that its outer layers are not fully settled. The star pulses, expands, and contracts in small cycles. Some astronomers believe these pulses are early warning signs of the dramatic changes that will eventually transform the star into a red supergiant. But for sheer size, Lambda Orionis is small compared to other stars in the same general region. There is one giant in particular that makes Betelgeuse look modest. In the constellation Cephei, just outside the Orion region but in the same general part of our galactic neighborhood, sits a star so deep red that the astronomer William Herschel called it the Garnet star when he first observed it in 1783. Its formal name is Mu Cephei, and it makes Betelgeuse look like a runner-up. Mu Cephei is roughly 2,800 light-years from Earth. Distance matters here, because despite being more than 4 times farther away than Betelgeuse, Mu Cephei is still visible to the naked eye. That is a clue to its sheer brightness. Estimates put the luminosity at around 270,000 times the output of our home star, possibly more. But the truly staggering number is the size. Mu Cephei has a radius around 1,000 to 1,500 times that of our home star. If you placed it where our home star sits, the surface would extend out somewhere between the orbit of Jupiter and the orbit of Saturn. Light, traveling at 186,000 miles per second, would take more than 2 hours to cross the diameter of this single star. That is hard to picture. So try this. A passenger jet flying at 500 miles per hour would need around 12,000 years to fly across the diameter of Mu Cephei. Human civilization, all of it, is shorter than that. The total length of recorded history would not get a plane across the surface of one star. Mu Cephei is also burning through its fuel at terrifying speed. Like Betelgeuse, it has moved past hydrogen fusion and is now fusing heavier elements deeper inside its core. The star is in the late stages of red supergiant life. It will eventually collapse and explode as a supernova, possibly within the next million years, possibly sooner. There is something else happening to Mu Cephei. The star is shedding its outer layers at a rapid rate. Astronomers estimate the mass loss at roughly 1/1,000,000th of the home star mass per year. That sounds slow until you do the math. Over 1,000,000 years, the star will shed an entire home star worth of material into the surrounding space. The shed gas forms a thick, dusty envelope around Mu Cephei, glowing in infrared light, slowly expanding outward. The envelope is part of why the star looks so deeply red. Dust in the envelope absorbs the bluer wavelengths of light coming from the star and re-emits them at longer, redder wavelengths. So the famous garnet color is not just from the star's own surface temperature, which is already quite cool by stellar standards at around 6,000 degrees Fahrenheit. The dust shroud amplifies the redness, turning Mu Cephei into the deepest red star, easily visible to amateur astronomers. Mu Cephei is also a pulsating variable star. It expands and contracts in a roughly 2-year cycle. As it expands, the surface cools and the star dims slightly. As it contracts, the surface heats and the brightness rises. The pulses are gentle compared to some variable stars, but they reveal that the star's outer layers are not in stable equilibrium. The whole stellar structure is wobbling toward eventual collapse. Even Mu Cephei is not the largest known star. There is one even bigger, sitting in the constellation Canis Major, that breaks comprehension entirely. Roughly 3,800 light-years from Earth, in the constellation Canis Major sits a star so vast it forces astronomers to invent new categories. It is called VY Canis Majoris. The classification is red hypergiant, a level above red supergiant. And the numbers attached to this star do not feel real. VY Canis Majoris has a radius estimated at roughly 1,400 to 1,600 times the radius of our home star. If you placed it where our home star sits, its surface would extend out to roughly the orbit of Saturn, possibly farther. Saturn. Light from the center of VY Canis Majoris would take more than 6 hours to cross the diameter of this one stellar body. To put that in scale, consider this. If our home star was shrunk to the size of a basketball, VY Canis Majoris would be larger than a stadium. A football stadium with the basketball at the center, and the stadium walls representing the surface of the hypergiant. The empty space inside the star, the volume between center and edge, could hold trillions of home stars stacked together. The mass is harder to pin down. Astronomers estimate it at roughly 17 times the mass of our home star, though some estimates run higher. That mass-to-volume ratio is bizarre. The outer layers of VY Canis Majoris are so spread out that the gas density at the surface is lower than the air pressure inside a vacuum chamber on Earth. You could pass through the outer atmosphere of this star and barely feel any matter at all, even though the heat would vaporize you instantly. VY Canis Majoris is also unstable. The star sheds its outer layers at a violent rate, far faster than Mu Cephei. Hubble images show the star surrounded by complex shells of ejected gas and dust, twisted into knots and arcs from previous eruptions. The surrounding nebula stretches roughly 1 light-year across. Some of the ejected material moves outward at 100 miles per second. These are not gentle losses. The star is essentially throwing chunks of itself into space. Astronomers also suspect VY Canis Majoris may be on the verge of a particularly strange kind of death. Most red hypergiants eventually collapse into supernovae and leave behind neutron stars or black holes. But VY Canis Majoris may be massive enough and shedding material rapidly enough to produce something called a failed supernova. In that scenario, the core collapses directly into a black hole without producing a bright outer explosion. The star would simply wink out. Most of its mass would vanish into the new black hole with only faint optical signs of the collapse. If that happens, an enormous star, one of the largest in the known galaxy, would disappear from the night sky over the course of a few months. No supernova fireworks, just a sudden dimming, then darkness. Imagine watching one of the largest stars in the galaxy simply vanish. VY Canis Majoris also tells us something about how stars age. The standard model of stellar evolution does not predict stars this big or this unstable. The star pushes against the theoretical upper limits of how massive a stellar object can be while still holding itself together. Some calculations suggest stars cannot exist at this scale without falling apart. Yet, VY Canis Majoris exists anyway, defying the predictions of theoretical astrophysics. But there is one more candidate that may break even VY Canis Majoris in size. Roughly 20,000 light-years from Earth, embedded inside a dense cluster called Stephenson 2, sits a candidate for the largest known star in the universe. Its name is Stephenson 2-18, and if the measurements hold, it makes VY Canis Majoris look modest. Stephenson 2-18 has an estimated radius of around 2,150 times the radius of our home star. Some estimates push that number even higher. Place it where our home star sits, and its surface would extend out past the orbit of Saturn, well into the realm where Uranus orbits. Light would take roughly 9 hours to cross from one side of the star to the other. Imagine that, 9 hours of light travel just to span a single stellar body. A photon leaving the center of this star at the speed of light would still be inside the star 9 hours later. If you sent a radio signal across the diameter, the message would reach the far side around the time most night shifts end on Earth. The star sits in a crowded region of the galaxy called Stephenson 2, a stellar cluster discovered in 1990. The cluster contains around 24 red supergiants and at least one red hypergiant, all packed together within a relatively small volume. This concentration of late-stage massive stars is unusual. Most red supergiants are scattered, but Stephenson 2 clusters them together, like a graveyard waiting to happen. Each member is approaching the end of its life. Each one will eventually explode as a supernova. Stephenson 2-18 itself is the most extreme member of the cluster. The star is roughly 440,000 times more luminous than our home star. That number is hard to grasp. If you replaced our home star with Stephenson 2-18, every planet in our solar system would be vaporized within minutes. The radiation alone would strip atmospheres, boil oceans, and melt rocky surfaces. Now consider the uncertainty. The size estimates for Stephenson 2-18 vary widely depending on the measurement technique. Some studies place the radius lower, around 1,500 times the home star. Others push it past 2,000. The reason for the spread is distance. Stephenson 2-18 sits in a part of the galaxy heavily obscured by dust and gas. Our view is partial. Astronomers must combine indirect measurements, infrared brightness, and modeling to estimate the size. The numbers carry significant error bars. Even with the lower estimates, however, Stephenson 2-18 is enormous. It belongs to a tiny class of stars that exists near the theoretical upper limits of stellar size. Computer simulations suggest stars cannot grow much larger than roughly 1,500 home star radii while remaining stable. Stephenson 2-18 sits at or above that threshold, depending on which estimate you use. The star is essentially defying the limits of what stellar physics says should be possible. Like other red hypergiants, Stephenson 2-18 is shedding material rapidly. Its outer atmosphere bleeds into space, forming a dusty envelope that further obscures direct observation. Each year, the star loses a measurable fraction of its mass. Over 1 million years, it will lose enough material to reshape the surrounding region of the galaxy. The end will come as a supernova, possibly within the next several 100,000 years. The blast will rival the largest supernova ever recorded. From Earth, 20,000 light-years away, the explosion would still be visible to the naked eye for weeks. But not every massive star ends quietly. Some tear themselves apart while still alive. About 15,000 light-years from Earth, in the constellation Sagitta, a star called WR124 is in the process of destroying itself. It belongs to a rare class called Wolf-Rayet stars, and the way it is dying is unlike anything else in the galaxy. Wolf-Rayet stars are massive. They are also unusually old by massive star standards, having burned through most of their hydrogen and exposed their inner helium and nitrogen layers to space. The outer atmosphere of a normal star shields the deeper layers from view. In a Wolf-Rayet star, the outer layers have been blown away by violent stellar winds, leaving the hotter, brighter inner regions exposed. WR124 is one of the most photographed Wolf-Rayet stars in the sky. The James Webb Space Telescope released images of it in 2023, showing the star at the center of a vast, complex nebula of expelled material. The surrounding cloud is the star's own former atmosphere, blown into space at speeds reaching 120 miles per second. The numbers behind WRS 124 are violent. The star is roughly 30 times the mass of our home star, and it is losing mass at a rate roughly 100,000 times faster than our home star does. In a single year, WR 124 ejects enough material to equal the entire mass of Earth, and it does this every few years. The accumulated loss has already amounted to roughly 10 home star masses worth of material, all of it now drifting outward in the surrounding nebula. The nebula itself is around 6 light-years across. It is studded with knots of denser dust, twisted filaments, and asymmetric arcs. The shape is irregular because the star does not eject material evenly. Some directions get more, some directions get less. The result is a chaotic, lumpy cloud rather than a clean spherical shell. What makes Wolf-Rayet stars important is what they tell us about the chemistry of the universe. The material they eject contains heavy elements forged inside the star's core through nuclear fusion. Carbon, oxygen, neon, and nitrogen are all produced inside massive stars and released into space when the star sheds its outer layers or eventually explodes. Wolf-Rayet stars are some of the most efficient distributors of these elements. The carbon in your body, the oxygen you breathe, the nitrogen in your DNA, much of it traces back to massive stars like WR 124, ejecting material into the galaxy long before our home star formed. The end is coming for WR 124. Wolf-Rayet stars do not last long. The star is probably within a few 100,000 years of its final supernova. When it goes, the explosion will be spectacular. Some Wolf-Rayet stars produce a particularly violent kind of supernova called a type Ike, which can sometimes generate the brightest known explosions in the universe, called gamma-ray bursts. These bursts release more energy in seconds than our home star will emit in its entire lifetime. If WR 124 produces a gamma-ray burst aimed in the wrong direction, the radiation could affect life on planets thousands of light-years away. Earth is probably safe. The star's rotational axis, which determines the direction of any potential gamma-ray burst, does not appear to point at us. But Wolf-Rayet stars are not the only stars that nearly explode. Some explode and somehow survive. 7,500 light-years from Earth, in the constellation Carina, a star called Eta Carinae nearly killed itself in 1843. The eruption was so massive that it briefly became the second brightest star in the entire night sky, despite its enormous distance. It ejected the equivalent of 10 home star masses worth of material into space, generating a structure that astronomers now call the Homunculus Nebula. And then, somehow, the star survived. That fact is what makes Eta Carinae one of the most studied objects in modern astronomy. By every theoretical model available in the 1840s, an eruption that violent should have destroyed the star entirely. The energy released was comparable to a small supernova. The mass ejected was enough to build several home stars. And yet, after the eruption faded, Eta Carinae was still there, weakened, surrounded by its own ejected gas, but alive. Astronomers call this kind of event a supernova imposter. The star imitates a supernova in brightness and energy output, but does not actually destroy itself. Only a handful of supernova imposters have ever been observed. Eta Carinae is the most famous example. The star is actually a binary system. Two massive stars orbit each other in a tight, elongated orbit, lasting roughly 5.5 years. The primary star is a luminous blue variable, a class of star known for unstable behavior and occasional violent eruptions. The companion is a hot, massive star somewhat smaller than the primary. The two stars exchange material across the orbit, with stellar winds from each one slamming into the other. The Homunculus Nebula, the structure created by the 1843 eruption, is one of the most beautiful objects in the night sky. It looks like two glowing lobes of gas, separated by a thin equatorial disk, like an hourglass made of light. The lobes expand outward at roughly 400 miles per second. Inside the nebula, complex turbulence and shock waves continue to generate observable activity nearly 2 centuries after the original eruption. But Eta Carinae is not done. Astronomers have detected smaller eruptions in the years since the great event. In 1941, the star brightened again briefly. In 2013, instruments detected another minor outburst. Each event suggests the star remains unstable. The next major eruption could come at any time. There is also the possibility that Eta Carinae will eventually go supernova for real. Some models suggest the star is approaching the end of its life. When it finally collapses, the explosion could outshine our entire galaxy briefly, and the gamma-ray output could be intense. Earth is far enough away that we are probably safe, but the supernova would be visible in daylight for weeks, then fade slowly over months. What makes Eta Carinae philosophically interesting is the question of why it survived the 1843 eruption. Theoretical models can describe what happened, sort of, but cannot fully explain how a star can release that much energy and still hold itself together. The physics is incomplete. The star is, in essence, an example of stellar behavior we do not fully understand. But for every massive star that survives, others do not, and the corpses of dead massive stars are even stranger than the living ones. In 1054, Chinese astronomers and observers across the world recorded a new star appearing in the sky. It was bright, visible during the day. It glowed for nearly a month before slowly fading from view. They had no idea what they were watching. They were watching a star die. That dying star is now the Crab Nebula, and it is the cleanest preview we have of what Betelgeuse will eventually become. The Crab Nebula sits roughly 6,500 light-years from Earth in the constellation Taurus. It is the expanding wreckage of a supernova explosion that occurred when the original star, a massive red supergiant similar to Betelgeuse, ran out of fuel and collapsed inward. The collapse happened in seconds. The outer layers crashed onto the dense core, rebounded violently, and were hurled outward at speeds approaching 10% of the speed of light. The result is a nebula about 11 light-years across, still expanding nearly 1,000 years later. Inside the nebula, complex filaments of glowing gas form a chaotic web of red, orange, and blue strands. The colors come from different elements ionized at different temperatures. Hydrogen produces red and pink. Sulfur and nitrogen produce other shades. The overall structure looks alive in long exposure images, like the brushstrokes of a violent painter who could not stop layering details. At the center of the Crab Nebula sits the corpse of the original star. It is now a neutron star, an object so dense that a teaspoon of its material would weigh roughly 6 billion tons on Earth. The neutron star is also rotating, spinning 30 times every second. Its strong magnetic field accelerates particles to near light speed, and those accelerated particles emit radiation in pulses every time the spinning star sweeps its beam past Earth. This kind of pulsing neutron star is called a pulsar. The Crab pulsar is one of the most studied objects in astronomy. It pulses across nearly the entire electromagnetic spectrum, from radio waves to gamma rays. Each pulse is a snapshot of physics operating at conditions impossible to replicate on Earth. The neutron star itself is roughly 12 miles across. Its mass is around 1.5 times the mass of our home star, packed into a sphere the size of a small city. Surface gravity is 200 billion times stronger than Earth gravity. If you somehow approached the surface, the tidal forces would stretch you into a thin stream of atoms before you got close. The Crab Nebula also contains evidence of recent activity. Hubble and other observatories have caught structures inside the nebula moving in real time. The pulsar at the center occasionally fires bursts of high-energy particles that ripple through the surrounding gas, briefly brightening sections of the nebula. The corpse is not entirely quiet. It still affects its surroundings nearly 1,000 years after the original explosion. When Betelgeuse eventually goes supernova, the result will look something like the Crab Nebula, a vast, expanding cloud of glowing gas with a dense neutron star or black hole at the center, slowly fading and spreading over thousands of years. Future astronomers will study Betelgeuse the way we study the Crab today, examining the wreckage of an event none of them lived to see directly. But not every neutron star is content to spin quietly. Some of them have magnetic fields strong enough to physically rip atoms apart. Of all the corpses that massive stars leave behind, the strangest are called Magnetars. They are neutron stars, just like the one at the center of the Crab Nebula, but their magnetic fields are about 1 trillion times stronger than the magnetic field around Earth, and roughly 1,000 times stronger than the magnetic fields of normal neutron stars. That number is hard to comprehend, so consider what such a field does to matter. If you brought a credit card within roughly half the distance from Earth to the moon of a magnetar, the magnetic field would erase the data on the card. If you brought a human within roughly 600 miles, the field would distort the electron orbits inside every atom of your body, twisting the chemistry of your cells until biology stopped working. The field would tear apart molecules at the quantum level. You would die before any conventional physical effect, like heat or radiation, had time to kill you. Around 30 magnetars have been confirmed in our galaxy. That number is small, but most magnetars are probably hidden. Their magnetic fields decay relatively quickly on cosmic timescales, so any given magnetar only spends about 10,000 years in its most active phase. After that, the field weakens, and the object becomes a less unusual neutron star. What gives magnetars their extreme fields is still debated. One theory says they form from fast-rotating supernova progenitors, with the rapid rotation amplifying the original magnetic field during collapse. Another says magnetars form from binary star mergers, with 2 neutron stars combining into one and inheriting the combined magnetic fields. A third theory involves convection inside the newly formed neutron star, generating a dynamo effect that boosts the field to extreme levels. Whatever the cause, magnetars are violent. They occasionally produce short bursts of gamma rays and X-rays, called soft gamma repeaters. Some of these bursts are brief, lasting milliseconds. Others last seconds. The energy released in a single burst can exceed the total energy our home star produces in a year. The most extreme magnetar event ever observed came from a magnetar called SGR 1806-20. On December 27, 2004, the magnetic field of a magnetar called SGR 1806-20 suddenly snapped. The release of energy was so violent that it produced the brightest extrasolar event ever detected from Earth. The star is roughly 50,000 light-years away, on the far side of our galaxy, and the burst from its eruption hit our planet's atmosphere hard enough to register on instruments designed to detect distant events. The energy released in the first 1/10 of a second of the burst exceeded the total energy our home star would produce in 100,000 years. That is not an exaggeration. The numbers have been verified by multiple independent observatories. When the burst arrived at Earth, it briefly ionized the upper atmosphere on the daylight side of the planet. Satellites in low orbit registered electromagnetic effects. Some sensitive instruments on the ground detected the burst as well, though the human population was unaware anything had happened. The event passed in less than a second from our perspective. Now think about what that means. A burst from halfway across the galaxy, traveling 50,000 years at the speed of light, was still strong enough to physically affect Earth's atmosphere when it arrived. If the same magnetar were located much closer, say within a few thousand light-years, the burst would have damaged the ozone layer, possibly triggered atmospheric effects that disrupted weather patterns, and could have caused biological disruption. If the magnetar had been located within a few dozen light-years, the burst would have stripped away part of our atmosphere and irradiated the surface enough to cause a mass extinction. The thing is, the magnetar that produced this burst is just one of about 30 known magnetars in our galaxy. Most are quiet most of the time, but each one has the potential to fire an eruption like the 2004 event at any moment. Astronomers cannot predict when bursts will occur. The eruptions seem to result from the slow build-up of magnetic stress in the crust of the magnetar, eventually releasing in a sudden snap, similar to the way an earthquake releases tectonic stress on Earth, except scaled to cosmic energy levels. There are also some rare events, called giant flares, that release even more energy than the 2004 burst. Only 3 giant flares have ever been recorded in the history of modern astronomy. Each one came from a different magnetar. Each one was brief but extraordinarily luminous. The 2004 event from SGR 1806-20 is one of these 3. Some astronomers have theorized that magnetar bursts may have caused mass extinctions on Earth in the distant past. The fossil record shows several major extinction events that cannot be fully explained by known terrestrial causes. A nearby magnetar burst, if one occurred millions of years ago, would have left subtle isotopic signatures in geological deposits. Researchers continue to look for these signatures, but no definitive evidence has emerged yet. For now, the threat remains theoretical. The known magnetars are far enough away that even their largest bursts only produce minor atmospheric effects on Earth. But the possibility that one of them could erupt closer, or that a new magnetar could form within range, remains an open question. If you think a magnetar is the most extreme stellar corpse possible, there is one more category that takes destruction further. Some stars do not become neutron stars when they die. They become something with no surface at all. About 7,200 light-years from Earth, in the constellation Cygnus, sits one of the first black holes ever confirmed by astronomers. The system is called Cygnus X-1, and it is currently in the process of devouring a nearby star. Cygnus X-1 is a binary system. One member is a blue supergiant star, roughly 30 times the mass of our home star, glowing brilliantly in visible and ultraviolet light. The other member is invisible light. It is a stellar mass black hole, roughly 21 times the mass of our home star, packed into a region about 40 miles across. The two objects orbit each other every 5.5 days. Because the orbit is so tight, the black hole's gravity pulls material directly off the surface of the blue supergiant. The stripped material does not fall straight into the black hole. Conservation of angular momentum forces it to spiral inward, forming a flat, swirling structure called an accretion disk. The disk surrounds the black hole and feeds material into it gradually. Inside the accretion disk, material gets compressed and heated to extraordinary temperatures. The inner regions of the disk reach several million degrees, hot enough to emit X-rays brightly enough to be detected from Earth. That X-ray emission is how astronomers first identified Cygnus X-1 in the 1960s. The system gave off so many X-rays that researchers had to invoke an exotic explanation, and the black hole hypothesis was the only one that fit the data. For decades, Cygnus X-1 was the strongest candidate for a confirmed black hole, though the term black hole itself was still controversial in some circles. By the 1990s, the evidence had become overwhelming. The mass of the unseen companion was too high to be a neutron star, which has an upper mass limit of roughly 2.5 home star masses. Anything heavier than that, in such a small volume, must be a black hole. The black hole at Cygnus X-1 is also rotating at extreme speed. Astronomers have determined the spin rate to be very close to the theoretical maximum allowed by general relativity. The rotation drags space-time itself around the black hole, an effect called frame dragging. The disk of material spiraling inward gets twisted by this dragged space-time, producing complex gravitational and electromagnetic phenomena that are visible in the X-ray emission patterns. The blue supergiant is dying slowly because of all this. As the black hole strips away material, the star loses mass, which changes its evolutionary trajectory. Eventually, the supergiant will exhaust its fuel and collapse. When it does, it will probably go supernova, ejecting most of its remaining mass. The core may collapse into a second black hole, creating a binary black hole system that will eventually spiral together and merge. When two black holes merge, they release energy in the form of gravitational waves. These ripples in space-time travel at the speed of light and were first detected directly by the LIGO observatories in 2015. Cygnus X-1 could become a future source of detectable gravitational waves, possibly in millions of years, when its orbit decays enough for a merger. For now, the system continues its slow dance. The blue supergiant feeds the black hole. The black hole grows. The accretion disk glows in X-rays. And astronomers watch, learning what they can about an object that bends space-time so dramatically that nothing crossing the event horizon can ever return. But not every gravitational structure is a destroyer. Some are sculptors of stellar nurseries. About 7,500 light-years from Earth, deep inside the Carina Nebula, a vast pillar of dust and gas rises out of a chaotic background of glowing material. It is roughly 3 light-years tall. Its peaks and ridges look like a mountain made of mist. Hubble photographed it in 2010 and named it the Mystic Mountain. The image went viral. People around the world saw the photograph and called it one of the most beautiful structures ever imaged in space. Underneath the beauty, the Mystic Mountain is being torn apart. The pillar is sculpted by intense radiation from nearby massive young stars in the Carina Nebula. The radiation evaporates the outer layers of the pillar, similar to the process happening at the Horsehead Nebula. The pillar itself is dense enough to resist destruction temporarily. The dust and gas inside it shield the deeper interior from the worst of the radiation. So the structure survives, but only at the cost of its outer surfaces, which are being constantly eaten away. Inside the pillar, 2 newborn stars are firing massive jets of plasma into the surrounding space. The jets travel at hundreds of miles per second and stretch across light-years of distance. They are visible in Hubble images as bright streamers extending outward from the top of the pillar, terminating in shock fronts where the plasma collides with the surrounding gas. The jets are evidence that star formation is still happening inside the Mystic Mountain. The same radiation that is destroying the outer surfaces of the pillar is also compressing the inner gas, helping new stars form even as the structure dissolves around them. The contradiction is striking. The pillar is being killed and giving birth at the same time. The Carina Nebula itself is one of the largest and brightest nebulae in the entire night sky. It is visible to the naked eye from southern latitudes. It contains some of the most massive stars known, including Eta Carinae, which we visited a few chapters ago. The whole region is a chaos of stellar birth, stellar death, expanding shockwaves, and intense radiation. The Mystic Mountain is just one feature among many. Computer simulations suggest the Mystic Mountain has roughly a few 100,000 more years before the radiation strips away enough material to destroy it. By cosmic standards, that is a brief future. The structure is a temporary feature in the broader life of the nebula. In 1,000,000 years, no trace of the pillar will remain. The newborn stars inside it will have emerged, ignited, and begun their own contributions to the radiation field. The dust will have dissolved into the surrounding gas. The mountain will be gone. What replaces it, possibly, is yet another generation of stars and structures. The Carina Nebula will continue producing stars for tens of millions of years. New pillars will form as new dense regions condense. Old pillars will dissolve. The cycle will continue until the available gas is exhausted, at which point the nebula will go dark and merge with the surrounding interstellar medium. The Mystic Mountain is a snapshot of one stage of this cycle, a beautiful, doomed temporary structure standing for a brief moment in cosmic time. But as wonderful as cosmic structures are, some objects defy explanation entirely. One star 1,000 light-years away has been dimming in patterns that no theory can fully explain. In 2015, an astronomer named Tabby noticed something unusual in the data from the Kepler Space Telescope. A star in the constellation Cygnus, roughly 1,500 light-years from Earth, was dimming in patterns that did not fit anything in the existing catalogue of stellar behaviours. The star is officially called KIC 846, 2852. Most people now call it Tabby's star, after Boötes' first name. Here is what makes Tabby's star strange. Most stars dim slightly when planets pass in front of them. The dip is small, usually less than 1% of the star's brightness, and the timing is regular. Tabby's star, however, was dimming by up to 22% at irregular intervals. No planet could be that big. The dips lasted days, sometimes weeks. The pattern did not repeat in any predictable cycle. Multiple theories were proposed. The most exotic was the suggestion, briefly entertained by some researchers, that the dimming could be caused by an alien megastructure, specifically a Dyson swarm. The idea is that an advanced civilization could build vast arrays of solar collectors around their home star to harvest energy. As the swarm orbited the star, it would cause irregular dimming patterns from our viewpoint. That theory got serious attention briefly because no other explanation seemed to fit the data well. The researchers were careful to note that the alien hypothesis was speculative and should be treated as a placeholder until natural explanations could be tested. Most scientists involved emphasized that natural explanations were vastly more likely. Subsequent observations have shifted the picture toward natural causes. The leading current theory involves uneven dust clouds orbiting the star. Some hypotheses suggest that the dust may come from broken-up comets or asteroid material disturbed by the star's evolution. Other suggestions involve a partly disrupted protoplanetary disk, leftover material from the star's formation that is still present and uneven. The dust clouds would block different amounts of starlight at different times, depending on their distribution and motion. There is also a long-term dimming trend in Tabby's star that goes beyond the short-term dips. Photographic plates from the past century show the star has been gradually fading over decades. The cause of this long-term trend is even less well understood than the short-term dips. Some astronomers have suggested it could be due to the same dust clouds or to slow changes in the star's own atmosphere. Others remain skeptical of the dimming trend itself, suggesting it may be a measurement artifact rather than a real change. What makes Tabby's star philosophically interesting is the gap between what we see and what we can explain. The star is 1,000 light-years away, well within our galaxy, and we have access to high-quality data from multiple observatories. And yet, more than a decade after the original discovery, no single theory fully accounts for everything observed. The mystery has shrunk, but it has not vanished. This is not unusual in astronomy. Many objects produce patterns we do not fully understand. Tabby's star is just an unusually well-observed example. The lesson is that even nearby cosmic objects can hide processes we have not yet figured out. But strangeness is not limited to single stars. Some entire galaxies look like they should not exist. 600 million light-years from Earth, in the constellation Serpens, sits a galaxy that should not be possible. It is called Hoag's object. Discovered in 1950 by the astronomer Arthur Hoag, the galaxy looks like a perfect ring of stars surrounding a glowing central core, with absolutely nothing visible between them. The central core is a yellowish-white spheroid of older stars, roughly 24,000 light-years across. The outer ring is a vast loop of younger blue stars, roughly 100,000 light-years across. Between the core and the ring is a wide gap of seemingly empty space. That gap is the puzzle. Most galaxies are either spiral, elliptical, or irregular in shape. None of those classifications produce a ring around a separate core. Hoag's object does not fit the standard categories. Astronomers have proposed a few explanations. The first theory says Hoag's object was created by a galactic collision. A long time ago, possibly 2 to 3 billion years in the past, a smaller galaxy plunged through the center of a larger one. The collision triggered a wave of star formation in the larger galaxy, which propagated outward as a shockwave through the surrounding gas. The shockwave collapsed material into new stars, forming the bright ring. The smaller intruder galaxy passed through and eventually dissolved or moved away. The result is the ring and core structure we see today. The second theory says Hoag's object formed naturally without any collision. Some extremely rare gravitational configurations could potentially produce a ring around a core in a single galactic system. This theory is less popular because the configurations required are unusual and difficult to produce in computer simulations. Most simulations that produce ring galaxies require collisions. There is also a third theory, which proposes that Hoag's object is actually a different kind of galaxy entirely, possibly a very old elliptical galaxy with a unique gas distribution history. This theory has fewer supporters but cannot be fully ruled out. What makes Hoag's object even stranger is that it is not unique. A small number of similar ring galaxies have been found, though Hoag's object remains the most striking and well-studied example. Some of these are clearly the result of collisions, with the intruder galaxy still visible nearby. Others, like Hoag's object, show no obvious sign of an intruder, leaving the formation process ambiguous. Hubble images of Hoag's object show another curiosity. Through the gap between the core and the ring, you can see another distant galaxy in the background, partially visible through the empty space. That background galaxy is far behind Hoag's object, possibly billions of light years further away. The combination of foreground ring, foreground core, and background galaxy creates one of the most striking images in deep sky photography. The ring of Hoag's object is also dynamic. The blue stars in the ring are relatively young, suggesting active star formation is still occurring. The ring may continue to evolve over hundreds of millions of years, possibly thinning out, possibly splitting into substructures, possibly dissolving entirely. For now, Hoag's object remains a beautiful anomaly, a galaxy that looks almost too perfect to be real, sitting 600 million light-years away, defying easy classification. But Hoag's object at least contains something. There are regions of space that contain almost nothing at all. About 700 million light-years from Earth, in the direction of the constellation Boötes, sits a region of space astronomers call the Boötes Void. It is roughly 330 million light-years across. Inside that vast volume, only a few dozen galaxies have ever been confirmed, where standard cosmology predicts there should be thousands. The void is not actually empty. Astronomers have catalogued around 60 galaxies inside it, but the density is dramatically lower than the surrounding regions of the universe. If you took our home galaxy, the Milky Way, and placed it at the center of the Boötes Void, the nearest galaxy outside the void would be so far away that its light would take tens of millions of years to reach us. The astronomer Greg Aldering once said that if our home galaxy had been inside the void, we would not have known other galaxies existed until the 1960s, when telescopes finally became powerful enough to detect them. How does a region this empty form? The standard theory involves the early universe. Shortly after the Big Bang, matter was distributed almost evenly across the universe, with only tiny fluctuations in density. Over billions of years, gravity amplified these fluctuations. Slightly denser regions pulled in more matter and grew into the galaxy clusters and superclusters we see today. Slightly less dense regions lost matter to their neighbors and grew emptier over time. The Boötes Void is one of those low-density regions, just on a much larger scale than expected. Its size is what makes it remarkable. Most cosmic voids are smaller, maybe 100 million light-years across. The Boötes Void is roughly 3 times that scale. Some astronomers have proposed that the void is actually the result of multiple smaller voids merging together over cosmic time. As the universe expands, voids grow. Adjacent voids can connect to each other if the boundary regions between them lose matter to surrounding clusters. The result would be a single large void where there used to be several smaller ones. This theory is consistent with the void's size and shape, which appear roughly spherical, but with subtle structure that may indicate merging history. The galaxies inside the void are also unusual. Some of them are arranged in what astronomers call a tube running through the void, suggesting they are part of a residual filament of large-scale structure that survived even as the surrounding region emptied out. The galaxies along the tube are separated by enormous distances, but still show some clustering relative to the otherwise empty space around them. Living inside the Boötes Void would be a strange experience. The night sky from a planet inside the void would look almost completely dark, with only the local stars of the planet's own galaxy visible. The other galaxies of the universe would be too far and too faint to see with the naked eye. Civilizations evolving inside the void would have a radically different cosmic perspective. They would not know about the universe outside their own galaxy until very advanced telescopes were developed. The Boötes Void remains one of the largest known regions of low density in the observable universe. It is a reminder that the universe is not uniform. Some places are crowded with galaxies. Some places are nearly empty. Some places, like the Boötes Void, are emptier than they have any right to be. But emptiness is not the only extreme. Some regions of the universe are so crowded that they birth stars at impossible rates. Roughly 5.5 billion light-years from Earth, in the constellation Phoenix, sits one of the most massive galaxy clusters ever discovered. It contains thousands of galaxies, vast amounts of hot gas, and a central supermassive black hole that is doing something so unusual that astronomers struggled at first to believe their data. The cluster is called the Phoenix Cluster. The black hole at its core is feeding on infalling gas at such an extraordinary rate that the surrounding region is producing new stars faster than almost any other cluster ever observed. Astronomers estimate roughly 740 new stars form in the central galaxy every year. For comparison, our own home galaxy produces only about 1 to 2 new stars per year. That difference is staggering. The Phoenix Cluster's central galaxy is birthing stars at a rate hundreds of times faster than our entire galaxy. What drives the difference? Most galaxy clusters contain enormous amounts of hot gas spread between the galaxies. The gas is heated to millions of degrees by gravity and the radiation from the cluster stars. At those temperatures, the gas is too hot to collapse into new stars. So most clusters do not form many new stars in their central galaxies. The central galaxy is usually a giant, slow-evolving elliptical galaxy that has stopped producing significant numbers of new stars. The Phoenix cluster is different. Something is allowing the hot gas in the cluster's core to cool more efficiently than expected. As the gas cools, it becomes denser and starts to collapse under gravity. The collapse produces new stars at the extreme rate observed. The supermassive black hole at the heart of the central galaxy plays a complex role. Most central black holes prevent star formation by emitting energy that heats up the surrounding gas, keeping it from cooling. The Phoenix Cluster's black hole, however, may be in a quieter phase. The energy output is not strong enough to heat the gas effectively. As a result, the gas can cool and the cluster can produce stars at the spectacular rate astronomers observe. The Phoenix Cluster also contains some of the most luminous gas known in any galaxy cluster. The gas glows brightly in X-rays, making the cluster one of the most luminous X-ray sources in the entire sky. The combined energy output of the cluster, including X-rays, ultraviolet, visible and infrared light, is enormous. The central galaxy itself is a massive elliptical galaxy that is rapidly evolving. The new stars being formed inside it are mostly young and blue, which is unusual for elliptical galaxies. Most ellipticals are dominated by older, redder stars that have already gone through their main hydrogen-burning lifetimes. The Phoenix Cluster's central galaxy is bucking that trend, with a wave of new young stars freshly emerging. What will happen next is unclear. The black hole could become more active in the future, heating up the surrounding gas and shutting down the star formation. Or the cooling could continue for billions of years, producing one of the most massive young stellar populations in the universe. The system is currently in a rare and possibly temporary state, which is why it is so valuable for study. The Phoenix Cluster reminds us that galaxies and their central black holes are deeply connected. Black holes do not just sit passively at galactic centers. They actively shape the surrounding environments, sometimes triggering star formation, sometimes shutting it down, sometimes producing the most luminous events in the universe. But the most luminous events of all come from a different category of object entirely. When astronomers first detected radio signals from objects called quasars in the 1950s, they had no idea what they were looking at. The objects appeared as point sources of light, like stars, but with strange spectroscopic features that did not match any known stellar type. The name quasar comes from quasi-stellar radio source, meaning objects that look like stars but are not. It took years of research to figure out what quasars actually are. The answer turned out to be more extreme than almost anyone expected. Quasars are the central regions of distant active galaxies, powered by supermassive black holes feeding on enormous amounts of infalling material. The energy output of a single quasar can exceed the combined output of an entire galaxy of normal stars. Some quasars are over 1 trillion times more luminous than our home star. That is not a typo. Trillion. With 12 zeros, a single quasar can outshine an entire galaxy of hundreds of billions of stars. How is this possible? The supermassive black hole at the center of a quasar typically has a mass between millions and billions of times the mass of our home star. As material falls toward the black hole, it forms an accretion disk similar to the one around the Cygnus X-1 stellar black hole, but on a vastly larger scale. The disk heats up to extraordinary temperatures, sometimes reaching millions of degrees. The heat radiates outward across the entire electromagnetic spectrum, from radio waves to gamma rays. Some quasars also produce jets of material shooting outward from the black hole's poles. These jets travel at near-light speeds and stretch across millions of light-years. The most powerful quasar jets are visible across vast distances and can interact with the surrounding intergalactic medium, depositing energy into regions far from the original black hole. The most distant quasars known are also some of the brightest. They sit billions of light-years away, near the edge of the observable universe. Because light takes billions of years to reach us from these distances, we are seeing these quasars as they existed in the early universe, when the cosmos was much younger. The most distant confirmed quasar sits roughly 13 billion light-years from Earth, meaning we are seeing it as it was less than 1 billion years after the Big Bang. That fact creates a puzzle. To produce the luminosity we observe, the central black holes of these distant quasars must already have been enormous, with masses of hundreds of millions or billions of times that of our home star. Yet they existed when the universe was still young. There was barely enough time, by current models, for black holes to grow that massive in the available period. How they got so big so fast is one of the open questions of modern cosmology. Quasars also serve as cosmic lighthouses. Because they are so bright, astronomers can detect them across enormous distances. The light from a distant quasar passes through intervening galaxies and gas clouds on its way to Earth, and the spectrum carries information about everything it encountered along the way. By analyzing quasar spectra, researchers have mapped the distribution of matter in the early universe. Most quasars are no longer active. The black holes still exist, but the supply of infalling material has dropped, and the central engines have quieted. The galaxies hosting these dormant supermassive black holes are now ordinary galaxies, similar to our own. Our own galaxy may have been a quasar billions of years ago, with its central black hole feeding much more actively than it does today. The universe was once full of quasars. Now it is mostly quiet. But somewhere out in the dark, there is one feature that may be quieter than it should be. When you look at a map of the cosmic microwave background, the leftover radiation from the Big Bang, the entire sky glows almost evenly. The temperature is the same to within tiny fractions of a degree, varying by only a few millionths of a Kelvin from one place to another. The whole map looks like a smooth, faintly speckled wash of pale light. But there is one anomaly, a region in the southern sky in the direction of the constellation Eridanus, where the cosmic microwave background is colder than expected. By cosmic standards, much colder. The region is roughly 70 microkelvins cooler than the average temperature of the surrounding sky. This is called the CMB cold spot. The cold spot is real. Multiple satellite missions, including WMAP and Planck, have confirmed its existence. The temperature dip is not a measurement artifact. It is genuinely there, hiding in one corner of the sky, and it is much larger and much colder than statistical models predict should ever appear. What causes it? The leading theory is that the cold spot is the result of a vast cosmic supervoid lying between us and the surface of the cosmic microwave background. As the radiation passes through the supervoid on its way to Earth, the photons lose a tiny amount of energy due to the gravitational effects of the void. This effect is called the integrated Sachs-Wolf effect. It would slightly cool the radiation we receive from that direction. A supervoid has been found in the right region. It is called the Eridanus supervoid, and it is one of the largest known voids in the universe. Some estimates place its diameter at roughly 1 billion light-years, though others give smaller numbers. The void's size is enough, in theory, to produce a temperature dip in the cosmic microwave background. The problem is that the dip in the CMB is bigger than even the supervoid can fully explain. By standard physics, the Eridanus supervoid should produce a smaller cold spot than the one observed. The discrepancy is significant enough that some astronomers question whether the supervoid alone can account for the anomaly. This has led to alternative theories. One is that the cold spot is a statistical fluke, an extremely rare configuration of random fluctuations in the early universe that just happened to produce a notably cold region. The probability of this is low, but not zero. The most exotic theory is that the cold spot is a kind of bruise, the imprint of a collision between our universe and another universe in some larger multiverse structure. In some theoretical models of cosmology, multiple universes can exist alongside each other, occasionally interacting at their boundaries. If two universes had collided in our cosmic past, the impact could have left a signature in the cosmic microwave background. The cold spot, in this hypothesis, would be the bruise from such a collision. This idea is highly speculative. There is currently no direct evidence for other universes, and most cosmologists treat the multiverse collision hypothesis as a placeholder rather than a serious explanation. But the fact that the idea is even seriously discussed reflects how difficult the cold spot is to explain through more conventional means. The cold spot is unusual. It may yet turn out to be a statistical fluke. It may yet be fully explained by the supervoid hypothesis. But for now, it remains an open puzzle in cosmology, a small region of unusual cold in an otherwise smooth universe. But not all cosmic mysteries are quiet. Some flash brilliantly across the sky for milliseconds, then vanish. In 2007, an astronomer named Duncan Lorimer was sifting through old data from the Parkes radio telescope in Australia. He noticed a brief intense burst of radio waves that lasted only 5 milliseconds. The burst was hundreds of times more energetic than any radio signal previously recorded from a comparable timescale. It came from a direction outside our galaxy, and the source was not identified. That first detection became known as the Lorimer burst. It was the first known example of a category of cosmic phenomena now called fast radio bursts, or FRBs. In the years since, telescopes around the world have detected hundreds of additional FRBs. Each burst is brief, lasting milliseconds. Each burst releases an enormous amount of energy in radio frequencies, and most bursts come from sources that are billions of light-years from Earth. Some FRBs come from distant galaxies, others come from sources that are harder to localize. A few have been detected coming from within our own galaxy, allowing researchers to identify the likely source as a magnetar. the kind of extreme neutron star we visited a few chapters ago. A magnetar called SGR 1935+2154 produced a fast radio burst in 2020, providing the first direct evidence that magnetars can generate at least some of these signals. But not all FRBs come from magnetars. Some bursts have properties that magnetar models cannot fully explain. Some are repeating, emitting multiple bursts from the same source over months or years. Others are one-time events, never seen again. The diversity of the bursts suggests multiple kinds of sources may exist. Theories abound. One says many FRBs come from neutron stars in extreme magnetic environments, with magnetars being the most common type. Another says some FRBs may come from collapsing magnetars converting into black holes, releasing a final burst of energy as the transition occurs. A third theory says some bursts could be produced by cosmic strings, hypothetical defects in space-time, that would whip around at extreme speeds and emit radiation. There has also been speculation, mostly from outside mainstream astrophysics, that some FRBs could be artificial in origin. The idea is that an advanced civilization might use radio bursts as communication signals, or even as a form of propulsion. This hypothesis has very limited support among astronomers, and the leading current explanations point firmly to natural cosmic sources. But the hypothesis remains in some discussions, mostly as a way to ensure researchers consider all possibilities. What makes FRBs so valuable for astronomy is the way their radio waves interact with the intergalactic medium on the way to Earth. Different wavelengths of the burst arrive at slightly different times because of the way space itself slows them down differently. By measuring the time delays, researchers can estimate the total amount of matter the radio waves pass through during their journey. This has allowed astronomers to map the distribution of ordinary matter across vast volumes of space, including some of the elusive missing baryons that had previously evaded detection. So FRBs are both mysteries and tools. The exact mechanisms behind every burst are not fully known, but the bursts themselves, even when their sources remain uncertain, provide unique probes of the structure and composition of the universe. A new burst is detected somewhere in the sky every day. Most never have their sources identified. They come, they flash, and they vanish, leaving only their signatures in the data. We are still learning how to interpret what they are telling us. But for all the strangeness within the observable universe, the strangest question of all may be what lies beyond it. The universe has an edge, not a physical wall, not a barrier you could ever reach, but a limit on what we can ever see, even in principle. It is called the cosmological horizon, and it sits roughly 46.5 billion light-years from Earth, in every direction. That number sounds wrong at first. The universe is roughly 13.8 billion years old. How can the edge of what we can see be 46.5 billion light-years away? The answer is that space itself has been expanding the entire time, stretching the distance between us and the most distant light sources. The light we receive from the edge of the observable universe was emitted long ago, when the source was much closer. While the light traveled toward us, space expanded, carrying the source farther away. By the time the light arrives, the source is now at the much greater distance we calculate today. That is the observable universe, the region we can see. But the universe itself almost certainly extends much further, possibly infinitely, possibly into regions so far away that no light from them will ever reach us, no matter how long we wait. The universe outside our observable bubble is a region we have no direct evidence about, only theoretical projections. What might be out there? The simplest theory says the universe outside our observable bubble looks much like the inside. Same kinds of galaxies, same kinds of stars, same physical laws, just more of it, possibly infinitely more. By that view, our observable region is a tiny pocket inside a vastly larger universe, and we will never see most of it. Some theories go further. The eternal inflation hypothesis suggests that our universe is one of many that emerged from a chaotic, inflating background. Each universe in this picture is a separate bubble, with potentially different physical laws or constants. If true, there would be other regions of physical reality where the laws of physics behave differently than they do here. We would never reach them, but they would exist. A few ideas in modern theoretical physics propose that information from outside the observable universe can sometimes leak in subtle ways. The CMB cold spot, for example, has been speculatively linked to such theories, although there is no firm evidence to support the link. If true, we might already have detected indirect signs of other universes without realizing it. There is also the question of the future. The universe is expanding, and the rate of expansion is accelerating due to dark energy. Over enormous timescales, the acceleration will pull more and more distant regions out of our reach. Galaxies that are currently visible will, in the far future, recede beyond the cosmological horizon and become permanently invisible to any observer in our region. Eventually, billions of years from now, our galaxy and a few nearby galaxies will be the only galaxies any future observer in our region can see. The rest of the universe will have receded into permanent darkness. That is a strange ending. The universe, in some sense, is closing itself off. The observable universe will shrink over time as expansion accelerates. Information about distant regions will be lost. Future civilizations, if any exist in the far future, will look up at a much emptier sky than we see today. Betelgeuse, our starting point, sits a mere 650 light-years away. The journey we just took, from the dying giant on Orion's shoulder to the edge of everything we can ever see, has covered scales so vast that the original starting point now seems impossibly close. But every step of that journey was real. Every object exists. Every mystery is being studied right now by astronomers around the world. What lies beyond Betelgeuse is the rest of the universe, and what lies beyond the rest of the universe may be more than we can ever know.